Hello, my name is Ryan Jakeman, and I'm here to talk to you about gate-induced drain leakage current in MOSFET transistors. Gate-induced drain leakage current is the current that escapes through the thin gate oxide in MOSFETs at drain voltages that are extremely small and much less than junction breakdown voltages. I will cover the problems associated with gate-induced drain leakage, factors that influence it, and different designs that are affected by it. Solutions will be covered that are implemented to limit it, and it will cover cutting-edge research and potential for the future of reducing the negative effects associated with it. An in-depth analysis of GIDL and potential for circuits once it is mitigated. Alright, so moving on to the presentation. So, the outline of this presentation will be the introduction, characterization of GIDL, factors affecting GIDL current in thin body devices, impact of GIDL on DRAM retention, impact of GIDL on short channel MOSFET, impact of GIDL in vertically stacked nanowire FETs, impact of GIDL in CMOS submicrometer circuits, utilization of GIDL in 1T DRAM technology, suppression of GIDL in LDD MOSFET, and the conclusion and references. So, moving on to the introduction. Gate-induced drain leakage is a parasitic current present in field effect transistors, particularly in metal oxide semiconductor field effect transistors. It occurs when VDG potential and band bending are high enough to generate electron-hole pairs by valence to conduction band tunneling. A MOSFET is a device used mainly to amplify electrical signals to be used as a switch. They consist of four main parts, which are the gate, drain, the source, and the body. MOSFETs are currently the most widely used transistor in both analog and digital circuits today. They use doping to facilitate the flow of electrons through them, and the main doping profile include P-type and N-type silicon, and the electrons pass through them using what is known as tunneling. Since silicon or other devices of dielectric material are not preferred, this is the site where GIDL occurs. Electrons escape through band-to-band tunneling due to the very thin gate oxide of the transistor and cause the parasitic GIDL current. Moore's law states that over the history of computing hardware, the number of transistors in a dense integrated circuit has doubled approximately every 2 years. This has made GIDL a huge issue in the industry as more and more transistors are being utilized. It also means that the size of transistors is becoming so increasingly small that many quantum level occurrences are rendering them useless. As band gap length and mass of the dielectric material used decreases due to Moore's law, BBT increases, causing GIDL to increase. So, moving on to the characterization of GIDL. So GIDL was first characterized by the Berkeley group in the 1980s. It arises in MOSFETs due primarily to band-to-band tunneling that occurs between the drain and gate. GIDL prevents the drain from reaching the current of 0 when it's in its off state. And it's extremely difficult to model GIDL. There are many factors that influence it. Another issue with characterizing GIDL is that BBT modeling is extremely difficult, and it is hard to match electron extraction data with complex number simulations. And in the figure we can see that it achieves only a minimal off-state current. It cannot achieve 0. Factors affecting GIDL. It is well documented that BBT is the main factor that influences GIDL current. The presence of gate-induced high electric field entails the overlap of silicon energy bands and breeds the emission of minority carriers. The relationship of doping profile directly influences the prominence of GIDL. The GIDL current depends on temperature because band gap has a small temperature dependence. Oxide thickness determines the amount of tunneling that can occur, thereby increasing or decreasing GIDL. GIDL is independent of channel length unless it reaches nanoscale, where it is then subject to short channel effects. In the first figure, we can see that GIDL is dependent on temperature. In the second figure, we can see that GIDL is dependent on drain doping concentration. small area in which on region 2 you can see on the 155 that it is coming off that band is due to impact ionization current and is not attributed to GIDL. GIDL in thin body devices. When a MOSFET is scaled down to a channel length of 50 nanometers and below, GIDL becomes very difficult to manage and limits the ability to scale down transistors for modern technology. Thin body devices such as single gate, ultra thin body, and double gate transistors are excellent at reducing the effects of GIDL and thus are able to be scaled down effectively. They have the ability to have lower doping concentrations and a lower gate-to-drain bias in the transistor, which helps curb the effects of GIDL. In the first figure, you can see that in thin body devices, for different types, the single gate and the double gate, there is different amounts of GIDL current as compared to the bulk SI MOSFET. And you can see the profiles of these thin body devices in the second figure. Impact of GIDL on DRAM retention. For every generation over recent history, we have observed a doubling in dynamic RAM, random access memory, which is DRAM, in the retention time. So because capacitors slowly discharge, the charges will degrade over time unless it is periodically refreshed by a signal. GIDL becomes a huge factor in the transistors used for DRAM and can cause major degradation in DRAM's retention ability. It is projected that GIDL will become a more serious problem over time due to transistors consistently increasing in quantity and decreasing in size per chip of DRAM. One way to improve on this is to increase the effort to control the number and location of metal precipitates in the transistor and using thicker gate oxide for future DRAMs. This will curb the effects of GIDL and help limit the short channel effects. In the first figure, we can see a typical DRAM chip, and in the second, we can see the characterization of GIDL compared to Type 2 and Type 3 current defined in this section in the term paper. Impact of GIDL on short channel MOSFET. SOI devices with ultra-thin silicon film are extremely advantageous to the typical bulk SI MOSFETs, such as reduction in short channel effects and junction punch-through leakage currents. The off-state leakage current of the short channel MOSFET is the amplification of GIDL current due to its floating body structure. This causes severe constraints on SOI device design. Techniques used to reduce GIDL current in short channel MOSFET include the reducing power, supply voltage, junction temperature, sub-threshold slope, and junction area. And in the figure we can see the tunneling of electrons and the profile of the short channel SOI devices. The impact of GIDL in vertically stacked nanowire FETs. One new proposed technology that hopes to eliminate short channel effects is the vertically stacked nanowire FETs, VSNW for short. VSNWs provide excellent gate controllability and high packing density and may be the final solution to the issues of the ever-shrinking transistor. Studies have determined that VSNWs are able to balance excellent low-off with high on-state characteristics. GIDL, which is an inevitable result, is ironically attributed to their excellent gate controllability. VSNW FETs have two different operational modes, IM and JM. The GIDL current is larger in the VSNW IM FETs than in the JM FETs. It was determined that the difference between the two types of nanowire FETs could be caused by the different doping concentrations in the extension regions. GIDL increases linearly with the stacking of NWs. In the first figure we can see the profile of the nanowire FETs and their effects You can see on the second, you can see that the IM operational mode of the nanowire FET is higher than the JM in the second figure. Impact of GIDL in CMOS submicrometer circuits. Technology scaling is the main cause of the reliability problems of submicrometer CMOS logic circuits. GIDL is a major constraint regarding off-state current in scaled-down CMOS devices for DRAM as well as electrically erasable programmable read-only memory (EEPROM) applications. GIDL current is also a serious problem in scaled CMOS digital VLSI circuits. A poorly designed standard cell library for VLSI application can have catastrophic effects due to high GIDL current. In an effort effectively to avoid the BBT leakage, it was proposed to form a space or gap between bird's beak of LOCOS isolation and edge gate of gate conductor line. Thinning of gate oxide, increasing of substrate doping concentration in LDD and drain regions augment the electric field dependence of GIDL. And you can see an EEPROM profile with GIDL's effects illustrated in the figure. A newer technology has emerged due to the situation called capacitorless 1T DRAM, which utilizes a floating body cell of a partially depleted SOI MOSFET as a storage node. This has been an effort to curb the effects of GIDL in DRAM, which are a major problem in retention time. So this technology effectively eliminates the rather complicated storage capacitor and giving it good process compatibility with logic devices. The 1T DRAM cell uses impact ionization current for write operations, which results in a higher writing speed but also higher power consumption. It helps take an aspect of transistors in DRAM that is conventionally very frustrating and use it as a tool to store memory. GIDL current should be very promising embedded memory for low power and high speed systems on chip. In the figure we can see 1T DRAM technology and how it can write ones and zeros using GIDL current. We can also see the time it takes to write the ones and zeros over time in respect to VG and VD. Suppression of GIDL in LDD MOSFET. Many lightly doped drain LDD and graded gate oxide GGO structures have been studied as potential solutions for the GIDL problem. The drawback with these devices, however, is that they exhibit poor hot electron reliability because of the reduced gate control in the lightly doped drain region. As a solution to this problem, fully gate-overlapped LDD devices have been proposed, such as TOPS. GIDL current in LDD devices is dependent upon gate oxide thickness, phosphorus dose, and spacer length. For smaller N concentrations, LDD devices will have a smaller GIDL current than both TOPS and SD devices. However, for large N concentrations, the difference in GIDL current between the devices is reduced. The new quasi-two-dimensional model has been applied and found that built-in lateral field plays a large role in determining the dependence of GIDL on drain doping profile and spacer length. You can see the TOPS device and its manufacturing process in the figure on the right. In conclusion, GIDL is a small parasitic current that stands in the way of scaling down transistors further. The job of scientists is to figure out ways to ultimately understand it and then either control it or eliminate it. With the continuous scaling of transistor-based devices, GIDL current is becoming a major problem in the industry and is being addressed further. Characterizing the GIDL concept, characterizing the concept of GIDL is difficult, and there are a multitude of factors that influence it. The effects of GIDL were analyzed in a multitude of different applications, and the action steps being taken to further understand and suppress it were described. In the future, I hope that we can fully understand GIDL and then use it in order to improve our current technology. Here are my references, and you can find out more information in my term paper. Thank you. Again, I'm Ryan Jaquin. I am an electrical engineering student at the University of Buffalo, and thank you for your time.